In a previous week, we learned about when you get an indeterminate form. So when you're solving a limit and you get 0 over 0, you're supposed to manipulate the equation more so that you can simplify it or do something so that you actually get an answer. So we're not okay with having 0 over 0 as the answer for a limit. So as a rule of thumb, the indeterminate form arises when you have two forces pulling in different directions. So what that means is as you approach 0 in the numerator, the fraction is getting smaller. So for example, like 1 over 1,000. So 1 is getting close to 0, and it's over something bigger, that's getting close to 0. But approaching 0 in the denominator, so if I had like 1,000 over 1, so now the denominator is getting closer to 0, our fraction just got bigger, so this one's going to 1,000. So indeterminate means you have to figure out which force is going to win. So is approaching 0 in the numerator or the denominator going to win? So the first set I want to look at are these 7 examples. So 4 of these are going to be determinate and 3 are indeterminate. So I want you to pause the video and just think about it. Which ones do you think are indeterminate and which do you think are determinate? All right, drum roll. The final answer is these 3 are actually the indeterminate forms. So these are the ones that you're going to have to manipulate more to figure out what exactly the answer is going to be, while these 4 are determinate. So we could actually say these either go to infinity, they do not exist, or they equal 0. So you may not believe me that these 3 are indeterminate, so I have some examples to prove it. So in one example, so for infinity over infinity, here's a limit that would be infinity over infinity. So if I plugged infinity in for x and for x squared and then for x, I would get infinity. Notice if I were to simplify this, x squared is on the top, and I have an x on the bottom, so I could simplify this into just an x. So if you plug in an infinity, that equals infinity. When you have an infinity on the bottom, or when you have x over x squared, originally when you plug in infinity for both, that's going to go to infinity. But if you were to simplify this one, you're left with 1 over x. So if we have 1 over x and you plug in infinity, that's going to be 1 divided by a huge number, so that's going to 0. So hence this is indeterminate because you're not always going to get the same result. So in one of these instances we got infinity, in the other instance we got 0. So when you don't get the same result every time, that's going to be an indeterminate case. Same thing with infinity minus infinity. So here I have x cubed minus x. So if I were to plug in infinity, we would get infinity minus infinity, but it's like a bigger infinity minus an infinity, so it's still going to infinity. Here, if we had infinity minus infinity, those ones are more like the same, so that's going to 0. So these were not the same result, so this is also indeterminate. The final one is if you have 0 times infinity. So usually this is the hardest one for people to wrap their minds around. So what I wrote out is in this case, this part of my limit would go to 0 because I have 1 over infinity, and this part of my limit would go to infinity if I plugged in infinity. However, if I were to simplify this, so right now I have 0 times infinity. So if I were to simplify this though, I've got x, and now this is just an x, so 1 times x is x, and if I were to plug in infinity, we're left with infinity. On this example, I've got a greater degree on the bottom than on the top, so this would be like a 0, and then this is infinity, so we've got 0 times infinity. But if we simplify, if we multiply the tops, our numerators, we've got x squared over x squared, so my leading coefficients are 1, so this limit is going to 1. So once again, we don't have the same result, so 0 times infinity is also indeterminate. So before we had ways to manipulate equations, so different strategies that we can use if we get 0 over 0 with infinity are the same as before. So you could factor, you could multiply by a conjugate, you could get a common denominator. Another one that I would recommend is maybe just graphing it. So you could pull out Desmos, just graph it and see if you can tell what it's doing as x goes to infinity or negative infinity. So if I look at this one, if I plug in negative infinity, we've got negative infinity minus negative infinity. So this one seems like it's going to be an indeterminate form. So if I plug in, if I try to manipulate this, my first thought is I see that I could factor out an x. So I'm left with x times x squared minus 1. I notice this is difference of squares. So now we've got x plus 1, x minus 1. So if we still have limit as x goes to negative infinity of this, we didn't really help our case much, because now it's just negative infinity times negative infinity times negative infinity. Not really sure what to do with that. So this is a case where I might look at the graph. I also could think, okay, negative infinity times negative infinity. Right now I'm really thinking that this one, if you do a negative times a negative times a negative, you're going to get a negative infinity. So I would probably say this one does not exist, and it goes to negative infinity. And we know from one of our determinate forms, infinity times infinity is determinate, so that one's not going to exist. So we basically put it in a situation where you're multiplying it all together, so it's not going to exist. If you didn't feel like doing all that work though, if you graph this is an x cubed graph. So an x cubed graph is going to look something like this. And as x goes to negative infinity, our graph is going to go down towards negative infinity forever as well. So that's another reason this is going to negative infinity. Our last two examples. In this one, if I plug in infinity and infinity and infinity, 1 over infinity goes to 0. 1 over 3 times infinity, so 1 over infinity again goes to 0. And then on the denominator, that's going to go to some huge number infinity. So what we're left with right now is 0 over infinity, and 0 divided by anything is going to be 0. So the limit of this function as x goes to infinity equals 0. So that one was a determinate situation. The last one I want to look at, if I plug in infinity here, I'm going to have infinity minus infinity, which I know is indeterminate. So I'm actually going to multiply by the conjugate. So I know normally we look at this kind of in the numerator or in the denominator, but today I'm going to do it in the numerator. So you keep whatever's in the square root the same. And I'm going to change this sign. So I'm going to make it a plus x and multiply that on the denominator as well. Because if you do it on the top, you have to do it to the bottom. So when I multiply this out, square root of x squared plus 1 times square root of x squared plus 1 is just going to give us x squared plus 1. And then because this is the conjugate, when I do this term and this term, those are going to equal 0 because one's positive, one's negative. So the last part is going to be negative x times x, which is minus x squared. And we're all over x squared, square root of x squared plus 1 plus x. And it's the limit as x goes to infinity. So if we were to simplify this, x squared minus x squared is 0. So we've got 1 over all of this. So essentially what we've got now is 1 over infinity. So if you have 1 over infinity, the bottom is getting a lot bigger than the top, so this limit is going to go to 0. All right, so now that you've seen some examples, why don't you guys try the practice problems, and hopefully it'll go well. Have a good day.